Alright, so let's talk about Kruskal's algorithm now. Right, so Kruskal's algorithm, where essentially the idea is extremely simple. We are still focused mainly on making the minimum cost spanning tree, right? So it again works on weighted undirected graphs, right? So that is basically what happens. But there's a very interesting quirk here that Kruskal's does not actually operate on a particular edge like D, G, or you can't actually do that. What you actually do is you call Kruskal on a particular graph itself, and what it does is that the first step is that it sorts. So it sorts all edges, and then the second step is that it adds edges. Add edge if it doesn't cause cycle, basically. If no cycle, I'm going to write caveman English, but you probably understand what that means, right? So let's go over the example and actually understand, because I mean you can read an algorithm and only really kind of understand what the words that it says. So let's go ahead. So the first step is to literally just make a list of all the edges and then sort them in ascending order, which is what I've done already in order to sort of save some time. And now what we're going to do is we're literally going to pick and choose our little edges, and yeah, that's basically about it. Like honestly, you don't even need to refer this diagram anymore since all the edges are listed already, right? And just to explain, so a comma b 7 simply means that there is a path from a to b which costs 7, and so on. That's basically what that means. So let's go ahead. So let's start with 1. So let's add this one. So we'll add a, we'll write b, we'll add a 7. Okay, this can be added, there is no problem. Now you'll notice immediately that this next one that you have to add, eg, does not connect to ab at all, and that is completely fine, right? You can just have that as well, completely okay. Next you have a ce which costs an 8, so no problem, we can add a ce which costs an 8, so that was added. Next we have a dg. Now again dg will be added, which costs a 9, right? Now next you have a cd, right? So cd is over here. Now notice what happens if you add this. If you add this, it becomes a cycle. Therefore dg will not be accepted at all. dg is not an acceptable edge. We will move to the next one, cd. Oh sorry, not dg, what am I talking? cd is not an acceptable edge at all, right? Because if you add cd, just as you noticed, it will actually end up in a cycle. Next we have ef. So f does not exist right now, so we'll just add an f, no problem. And ef costs a 10. Okay, so that is done, we added it happily. Now af is 1, right? So can we add af, right? So yes, we can add af. There is no cycle forming right now, so we can do that. Af will cost us 11, we can move on, right? So that is also good. Now bd, if we add bd, of course, if you add bd, it will cause a cycle, right? And also, I mean, here we can preemptively check, not preemptively, it happens anyways in the algorithm. You actually already have all the vertices, I think so. A, B, C, D, E, F, G. Yeah, so you have every single vertex possible. We don't even have to actually consider any of the rest, right? We can just stop after AF, and that is basically all. Kruskal will always result in the exact same MST that is possible for a single graph. Probably one of the more stable things. It's generally used for more sort of sparse graphs, while prim is the more acceptable thing that you would use for like very dense and highly connected graphs. So that is basically what we have here. And of course prims can be customized as well. If you only want a spanning tree from a particular vertex, you can do that, but in Kruskal's you have no such option. Kruskal just goes ahead, finds the global MST in a sense, and that is basically it. So yeah, that's about it.